Mr. Pulinez, thank you very much for joining us here. We're at the European Geosciences Summit, the General Assembly for 2011. And just yesterday, there were a number of presentations on the question of the different kinds of precursors in different domains of the electromagnetic spectrum, which we can use to hopefully at some point have a real, maybe even a forecasting capability for earthquakes. Anyway, let's discuss what you've been looking at. What is the significance of electromagnetic precursors to earthquakes in your work?
Okay, I prefer to talk not only on the electromagnetic precursors,
sure,
but it is the earthquake preparation is a complex physical, chemical processes happening starting from the earth crust up to the atmosphere and ionosphere. And they have a different kind of manifestations. Within the period, we are talking now about the short-term prediction, so it is something like few weeks up to few days and hours before the seismic shock.
okay,
And because it is this process which is generally connects many factors, we try to find approach which gives us opportunity to explain what is happening, why we see so many different variations or anomalies during this preparation period. The first reason is very natural. When you have release of energy which is equivalent to several thousand on nuclear bombs, so it is impossible to store this underground and in the one moment to release. The Earth is a living matter, and there are some processes storing of the stress. In this stress should manifestate itself in some parameters.
okay,
So the most natural is that when you have deformation, you have formation of cracks inside the crust, you change the system of the gas migration inside the Earth crust.
Sorry, can you repeat that?
You change the system of gas migration.
Gas migration.
Gas migration. The main components of this is a CO2, helium, hydrogen, and a radon, which is a radioactive gas, which is a product of the decay of uranium. It present everywhere. You know that for sanitarian purposes, when you build your house, you make the monitoring of radon to be safe in your house. It is a heavy, odorless gas, but it was detected many years ago that its release increases before the earthquake, because this gas migration carries this radon, and water coming up to the Earth's surface, aquifation. Probably you have seen the video from Japan showing like a water going up during and before the earthquake. So water also carries radon with it. And now starts the very interesting process which is characteristic for many natural events. For example, you know that now the variations of the cosmic rays are associated with the formation of the cloud coverage of our planet. Why? Because the cosmic rays produce ionization of water. The ions become the centers of condensation of the water vapor. Water vapor condensates on ions, and you obtain the nucleation, which with center of condensation for formation of clouds. The same is happening with coming of radioactive matter of radon on the ground surface, close to the ground surface, because radon is very heavy. It also produces ionization of air. Ions becomes the centers of condensation and forms the large clusters, this ion and envelope of many water molecules.
Yeah, you mentioned in your presentation
Yes.
the ionization process and the hydration of the ions.
Hydration, yes, because it is not pure condensation, because people who know physics very well should say that it should be saturation vapor to have condensation.
Okay.
But hydration does not need saturation. In any level of humidity, relative humidity of air, you will have the hydration on the ions. So 30% of humidity, still you will have hydration of ions. And when ions becomes, when molecules of water become too attached to the ion, they release their free energy when they were in air, which is named latent heat. And this is the latent heat is the source of the thermal energy, which is registered just over active tectonic faults. It could be monitored by the satellites. They show very nice the configuration of the active tectonic faults during the period of preparation of the earthquakes.
What period are we talking about?
We are talking about few weeks before the earthquake. We have activation of the tectonic plate where epicenter is situated. So we can see the heating of the borders between the tectonic plates and active tectonic faults. This is the smaller structures. So starting from the ground surface, we see the thermal anomalies along the active tectonic faults, which manifestates that we have release of radon along the tectonic faults. And geophysical perspective shows that we have peaks and maximum of radon concentration over tectonic faults. They are sources of the radon coming from the ground. So the first level, it is ground surface. Then this heat starts to be accumulating, and because you have temperature difference between the fault and the area outside the fault, so it starts the mixing due to temperature difference. You have the horizontal motion and convection motion, because the heater air tries to go up, and it is transformed into so-called small spirals. Chirality is forms the, and these small chiral structures tend to merge. It is in the theory of chaos, it's named as reverse cascade instability. They merge and form the large thermal spot, which could be registered in the upper layers of atmosphere.
Okay.
And simultaneously, this transforms of the latent heat is also could be registered by satellites. There is some products in the some NASA sites which give you directly the latent heat fluxes of a special region, and we were able to detect this latent heat fluxes before many earthquakes. For example, before Sumatra earthquake, the total energy integrated for the 4 days.
Which Sumatra?
Sumatra 2004.
2004.
2004. The total thermal energy released before the Sumatra earthquake, 1 order of magnitude was higher than the mechanical energy released during the earthquake itself. So you can imagine what a huge power is inside in the simple thing is the water vapor. From what people ask from what is the source. It is the sun. Sun prepares this water vapor because we have constant evaporation of humid from the rivers, from lakes, from source, and all the time we have this water vapor which contains this latent heat, and during condensation it is released. So the source of this energy is the sun. So, but now we come into electromagnetic.
Okay. Yeah.
So these thermal anomalies could be registered not only in the form of the heat like we measure by temperature, yes, but as a radiative heat, is the infrared radiation, which is in electromagnetic spectrum with the wavelengths from 8 to 12 microns. This is a window which is transparent for the clouds. And it is possible to measure even through the clouds, and what is doing Dr. Ozunov, it is measure this infrared emission at the top of atmosphere. It is something like from 8 to 12 kilometers.
Under the ionosphere? Or?
No, it is under the, no, ionosphere is much higher, it's 100 kilometers. Okay. It is 10 to 12 kilometers altitudes. And there were elaborated the very precise and special techniques using the measurements of previous, for example, for NOAA 20 years. We have very good background, and from this background we are able to estimate that in this place.
Sorry, so these precursors of these phenomena you've been 20 years, you said?
No, 20 years we have background of measurements to calculate the anomaly having this background.
All right.
We started our study more or less 10 years ago, according to this. And we are able to see the dynamics of the development of these heat anomalies on the top of atmosphere before the earthquake. These anomalies usually appears few days before the earthquake. And there are specific features that they are sitting over the area of the earthquake preparation. They can move a little bit exactly along the tectonic plates border or along the active tectonic fault, but are very close to the future epicenter. So this is the first very reliable signature of the approaching earthquake, and now we have very good statistics, very good score for this, for all recent major earthquakes. We have the data showing the appearance of this OLR anomaly, which is outgoing long wave radiation. OLR. For all, without any exclusion, we see over ocean, inland, near the shore, not depending where this epicenter. It is advantage in comparison with any other techniques of the precursors, because many of these precursors could be detected only inland. But because we deal with the gas which could be released from water as well, we see anomalies over the water. You can see here, 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 anomaly is sitting over the water.
Right. What instrumentations do you use to measure this?
It is infrared sensors which are installed on the majority of remote sensing satellites.
They all have them.
Like NOAA satellites, Aqua, Terra, it is a MODIS device, AVHRR in NOAA satellite, and similar devices, for example, on board the Russian Meteor satellite, we have the similar device. European satellites, every remote sensing satellite now has an infrared sensor, and we need the frequency band or wavelength band between the 8 and 12 microns. Now we are going upper. In the upper layers, it is ionosphere. Ionosphere, it is a part of our atmosphere, but partly ionized. Its ionization comes from mainly from ultraviolet radiation emitted by our sun. Some part is ionized by the X-rays and energetic particles. But so the main source of the ionization, it is ultraviolet radiation. So because we have radiation only during daytime, we have increase of ionization during daytime and decrease during nighttime, and the variations of electron concentration look like sinusoidal, you can see in daily variations. And it is studied for many, many years. We have very good models which explains the climatology of the ionospheric behavior. We also know very well the behavior in the sphere during the active solar events like solar flares, geomagnetic storms. For any point we have the regional models which can explain what will be behavior of the ionosphere during geomagnetic storms. So we know behavior of the ionosphere during quiet time condition and during geomagnetically disturbed condition. And starting from this, we are looking on some anomalies which are associated with the earthquake. How these anomalies in general can appear in the ionosphere.
Right.
We were talking about the...
You mean, so, because there could be different sources for...
No, the source is the same. Because when
That'll be
yes, I will explain. We live in electrical environment. We never think about this, but when you are standing here, it is a vertical electric field which has gradient 100 or 150 volts per meter. So between top of your head and your legs, you have potential difference 220 volts, like
the power source,
like a power source.
Yeah. Power jack.
The problem is that the conductivity of air is very low, so the current which we have inside the atmosphere is 10 powered minus 12 ampere per square meter.
Right.
What is the source of this potential difference? We have potential difference between the ground and ionosphere. This potential difference is created by the thunderstorm activity. All over the world we have the global thunderstorm activity in Africa, in America. Mainly thunderstorm activity is over the land. But it's not so important. The thunderstorm discharges provide the positive potential of the ionosphere in relation to the Earth.
Okay.
And we have the potential difference between the ground and ionosphere, something like 250 up to 500 kilovolts. And this potential difference is dropped in this bulk of atmosphere from ground surface up to more or less 60 kilometers. For this global electric circuit, usually they take the lower border of ionosphere near 60 kilometers.
Okay.
But the most potential drop we have in so-called boundary layer of atmosphere. Boundary layer, it is the layer where we have turbulent motion of the air. In the upper layers, we have no such turbulent motion. It is continuous gradient without mixing, which we have in the ground surface. And so you can imagine you have potential difference, you have a resistor, what is our atmosphere.
Right, okay.
And if you change the value of this resistor, it means if you change the conductivity of this layer, near ground layer, and this conductivity is changed by appearance of these ions produced by radon. First, you will observe the increase of conductivity, and then when these ions grow and become a large clusters which are not moving, it cannot carry the electrical current, you will have the drop of conductivity. Like, for example, in the sandstorms, when you have a lot of sand and dirty, for example, in dirty cities, the electric field larger than in open field.
Okay.
Because due to presence of the dust and aerosols, the conductivity drops. The same thing when you have formation of these large clusters, which were spoken before, the drop of conductivity leads to change of the ionospheric potential relative to the Earth.
Okay.
So ionosphere feels the earthquakes through the global electric circuit, through the change of conductivity of atmosphere.
Okay.
But the ionosphere is highly conductive media. It tries to maintain its equipotentiality. If you have a good conductor, all the parts of this conductor are at the same electrical potential. Okay. If something changes this rear, it tries to redistribute the electron concentration and ions to maintain its equipotentiality. What means redistribute? So their appearance, the drift or electric currents within the ionosphere, and you have a formation of irregularity over the area where you have anomaly of conductivity.
And that's what you've been talking about with the total electron content.
Yes. So, and parameters of the ionosphere could be measured by multitude of techniques. It is ground-based vertical sounding called ionozones. We can put the same ionozone on the satellite and it will be topside ionospheric sounding.
Okay.
You can measure the total electron content between the satellite and the ground. You can make the ionospheric tomography from the low orbiting satellites. So there are a lot of techniques. All of them were tested and all of them show the anomalies in the ionosphere.
Okay.
So also, okay, I have a book published in Springer, by Springer, which named Ionospheric Precursors of Earthquake. You can find there everything explaining what is happening. But I also can say that also for majority of earthquake we see ionospheric anomalies which are very close to these thermal anomalies in their position, and in time they are also coherent. But we see propagation of these anomalies from the ground surface up to the ionosphere. So usually the ionospheric anomalies appears one day later or the same day as the thermal one.
Now you have on this poster here some things related to specifically to the 9.0 earthquake in Japan.
Yes, it was a very difficult case for analysis for many reasons. One of them, that earthquake happened between two geomagnetic storms. One of the indicator of the geomagnetic storm, it is global equatorial geomagnetic index which is named DST. Okay, and this is a graph of this geomagnetic index. And when we have the sharp drop, it means the start of the geomagnetic storm. And then we have recovery phase, we have quiet geomagnetic condition, and then the next storm.
Right.
Which happened exactly in the moment of the earthquake.
So that's sort of very interesting, because
Yes.
that sort of brings up that, as with a lot of these things that we can't see directly, it requires that we need a broader range of sensory instruments as possible to correlate and make sure that we can annihilate things that don't have things.
Correlation of solar and geomagnetic
do directly with
activity
you.
with seismic activity is very difficult task, because
Maybe there's
statistically some people show the existence of the correlation, other people show that there is no correlation. It should be carried out very careful study of this. But I can confirm that very often it happens that geomagnetic storm is very close to the earthquake. And but
Mr. Duma said something about that.
Yes,
yesterday,
yes.
right?
But we cannot say that geomagnetic storm earthquake. No. Sometimes geomagnetic storms could be 1-2 days before the earthquake.
Sometimes after.
Sometimes 1-2 days after. Sometimes, like we have here, simultaneously with the earthquake. So it looks like we have the common source of origin which provokes both these events, and they have appear in the,
That's interesting.
In the close time. But why we, for example, interpret this like a precursor? Because here this effect of the geomagnetic storm, which is blue, should decay, because here we have quiet condition.
Okay.
But contrary to our expectation, we have the sharp growth of electron concentration on 8th of March. It is 3 days before the earthquake. And this is supported, the GPS tech, supported by the ionospheric tomography, which is another technique to study the ionosphere. It is a low orbiting satellites, and they have the two frequency transmitter on board, and you put on the ground like a line or chain of receivers which receive the satellite signal, and you can from this registration reconstruct the vertical cross section of the ionosphere in the plane of the satellite orbit. It like tomography. You have many rays between the satellite and several receivers.
Okay.
And you process by tomography technique this multitude of rays and reconstruct from this by special mathematical procedure the vertical structure. And this is a tomography reconstructions for the chain which is installed on the Sakhalin region, Sakhalin island of Russia, which is very close to the northern part of Japan. These receivers belong to the corporation Russian Space Systems. And our co-authors, Romanov, are responsible for this result. And they also observe the large positive anomaly, and again on 8th of March. So we have completely different techniques. It is GPS tech, this is a tomography, and they demonstrate the same thing. And next one, it is the ground-based ionozones. Ionozone, it is a radar working in the shortwave frequency band from 1 to 20 megahertz. It is broadcasting, and they actually were designed.
Is this what is called the very low frequency?
No, it is not a very low.
Sorry, what did you say?
It is HF, high frequency band.
Okay.
They are designed to
I didn't catch the number. Just can you repeat the number? The hertz number?
From 1 megahertz
Oh yeah.
to 20 megahertz.
Okay. Mm-hmm.
They were designed to monitor and predict the propagation of radio waves.
Okay.
When we had no VHF broadcasting and FM broadcasting in the 30s, 40s, 50s of last century, the broadcasting was in the HF wave band. And these devices were designed especially to monitor the state of the ionosphere, to predict the radio wave propagation in this frequency band.
Okay.
And now they used to monitor the space weather, because ionosphere is very sensitive to solar effects. And every country has its own network of the ionozones. Here in Japan, we have 4 ionospheric stations: Wakanai, Kokubunji, it is Tokyo, Yamagawa, and Okinawa. These 4 ionospheric stations. Here you have their coordinates. And we were able to elaborate the technique which shows that due to specific variability of the ionosphere before the earthquake, when you have station close to the epicenter and try to correlate this station with other station which is far from epicenter, the cross-correlation coefficient drops before the earthquake. And this is a cross-correlation coefficient between the Kokubunji, which is close to the epicenter, and Yamagawa station, which is far from the epicenter. So we have just the configuration described in our publication.
Okay.
And again, on 8th of March, we see the drop of cross-correlation coefficient, like in GPS tech and ionospheric tomography. So 3 independent techniques show the same for this earthquake. So 3 days before
3 days.
the main show. And the last result, we try to compare. So it's the same season, for example, of the year, and mainly more or less for the same solar activity, because the ionospheric density depends on the solar activity. But the last year, this year, not differ too much in this.
Okay.
So we took the variations of the electron concentration for year 2010, for period from 23rd of March to 23rd of February to 23rd of March. And for year 2011, for all 4 ionospheric stations. And simply we subtracted from 2011 the 2010 data. So they have, and this is a difference. So
can you just say quickly where the origin is of the what's originating the high frequency waves?
This is, I told you, this wave I emitted, it is like a radar. It is installation, it sends pulses to the ionosphere and obtains the reflection.
Okay, so and that's what these 4
yes,
measure.
yes.
Okay.
And on the different frequencies...
Where the radar is not...
No. Okay. Different frequencies are reflected on the different altitudes of the ionosphere. The higher electron density, the higher frequency you need to reflect from the ionosphere. Okay. So the ionozone is starting to send pulses from 1 megahertz and goes up to 20 and receives the reflections from the ionosphere. And specific frequency, which is named critical frequency, ionosphere is not able more to reflect the radio waves and they pass through.
Okay.
And this frequency is named critical. And this is a main parameters used by the ionozone, and we use just the critical frequency, which reflects the maximum electron concentration in the ionosphere. So, from year 2011, we subtract 2010.
Okay.
And you can see, starting from something like 5th of March,
Right.
increase and then decrease. And this is a moment of the earthquake.
Right.
So this is from north to south, Wakanai, Kokobunji, Yamagawa, Okinawa.
Yeah, pretty big spike.
Yes.
Pretty.
And
Okinawa,
then
Okinawa is a bit more erratic, but
yes, but Okinawa, it is low latitudes which are affected by a so-called equatorial anomaly, which appears in the equatorial ionosphere.
Okay.
So it's a little bit much higher variability than on the mid-latitude and such. So what I would like to underline more,
okay.
that our approach, it is a multi-parameter analysis. We can say that it's very difficult, almost impossible, to make some kind of prediction using only one parameter. For example, thermal, ionospheric, VLF propagation, so on, so on. But if you have something like we name synergy of the processes,
right.
we see that all of them are connected and show the same area with the same time interval. And we see some development of the processes starting from the ground surface, like the surface temperatures and air temperatures and top of atmospheres and ionosphere. And we see this dynamic, all this complex of the effect. We may say that this is a multi-parameter precursor of the earthquake. This is our approach.
And it's interesting because he noted that also with the geomagnetic storms poses the question, well, where's the physical cause? That still needs to be investigated.
Yes.
Where's the principled cause? But just one thing I wanted to say, because Professor Biaggi was saying that their main problem is they just don't have enough sensors. Like they have very few sensors. Through Europe, there's only 7, and if you had a global, global array of these things, then they could be looking where all the things are happening around the world.
This is a difference between ground-based measurements and satellite.
Yeah, you were saying you don't.
That with the satellite we have a global picture without exclusion. This is an advantage.
You're saying you have the instrumentation.
Yes.
Is that right? Do you?
Yes, of course we should.
Because right now we're seeing that NASA's getting huge cuts to its budget. There was the case of the.
It's very pity because we can develop this technology, and many other countries try to build their own satellites. For example, China now is on the way building specific aim-directed satellite to measure electromagnetic precursors of earthquakes, to be launched in 2014.
14,
yes. But I think, looking from the perspective what we have now in Japan, how tragic event, how many people in so developed country, okay, we can say that
Japan.
when you have
well
but this demonstrate that nature has no difference between the poor and rich country, developed, not developed. We cannot fight with nature. We cannot overcome it. It's very strong and disastrous event. So we need to make the urgent actions.
But we can understand it. That's the first step.
To start our activity now, we have demonstrated that we are able at least to make some kind of warnings. We not say about prediction, but we can say that in this area, in nearest few days, we expect some seismic shock, and we are able to even to estimate the future magnitude.
Mm-hmm.
So,
but
of course, many
clarify,
things are not clear, but we cannot prolongate in infinity our investigation. How many victims we need to continue our investigation?
I think it's very important. I think it's clear with the amount of victims we have to do it right now.
Yes,
that we should escalate.
We can.
The question that I have to you on that specifically is: do you have are all the instrumentations there in place that you need? And if you didn't have money restrictions, what would you want to see implemented so that you could immediately begin setting up things that we could use to recognize precursors all around the world, every nation along the Rim of Fire and beyond? What would you need for that?
Okay, in present moment, we have quite enough the remote sensing satellites, and many countries, including the United States, have the plans for example, in POIS project to launch more satellites having on board the infrared sensors.
So there was one called Destiny, which was supposed to measure. I'm not sure. I can't remember the acronym, but that was a satellite that was cut. That was actually not launched. Then you had the GOES-11, which was launched, I think, but they didn't have a ground crew to analyze the data. So it's up there doing stuff, but you don't have people analyzing the data. And one thing you mentioned before is that you've done this work, but there's only so much that 2 or 3 people can do.
In principle, we can start now if we will have at least some specific laboratory with the staff, more or less, I estimate like 10 people. It's enough to start to analyze the data on infrared, GPS tech, VLF propagation. It is enough to do some kind of warning, at least of some areas like California, Japan, Mediterranean, Mexico. We have enough instrumental means. It does not mean that we should not stop, it should not develop another types of measurements and increase our ground-based network. But we should take as an example the medicine. For example, the problem of cancer. It was thought that it is impossible to overcome. Then the doctors start to, one kind of cancer now is treatable, the second one, and it is expanded. Because people do not stop, they are doing what they can to do in the present moment.
Right.
And we should do the same. We should do with what we can to do in the present moment. But in present moment we need some support because we are very few. We are under pressure from different sources for different reasons. We need to live in quite good conditions to work, to have more human resources. I said something like 10 people laboratory. And I'm sure that we are now able to make a good progress improving this technology and elaborated the techniques, especially application techniques for the short-term warning. This is
great.
What I want.
You basically answered all my questions. I have just one more because I think Ben sent you some material on the kind of work that they've been looking into, especially looking at the records of fossil records showing biodiversity, volcanic activity from volcanic rock over just what we have, which shows some very clear cycles of 60 to 62 million years of increase and decrease of biodiversity and also increase volcanic activity at around the same time. And because you mentioned that there's also now these also the phenomena of the geomagnetic increased activity, which goes along with the things that you guys are measuring with some kind of phase shift maybe. Have you, just as a sort of a free question, has there been any thought, any any thoughts to look into that there's maybe an increase in general sensitivity within a longer time frame due to some external sources?
What we know from historical data, let's start from the shorter periods. For example, Maunder minimum of the solar activity. So in 16th and 17th century, you know that in Holland we had ice. We have a lot of literature showing that people
ice skating
and so, and now we have very warm. And from historical measurements of the solar activity, we have seen that it was very low, extremely low, not at all the 11 years solar cycle activity. What we observe now, we had extremely long period of low solar activity. It was not predicted by anybody. We had minimum which lasts at least 2 years or up to 3 years longer than it was expected. So the one reason there is some variability in activity of our star, which provides the life in the Earth. The second, which is more important and probably may have more grave consequences, it is reversals of the geomagnetic field. From paleogeomagnetic data, we have seen that the polarity of geomagnetic field was changed several times during the history of our planet. And this transition period is very dangerous because during transition we will have some period, nobody knows how long it will be, when we have almost no geomagnetic field.
There's no polarity, right? Is that what you mean?
Yes, it is flipping.
In flux.
Yes, and this geomagnetic field protects us from the extremely solar energetic particles and cosmic rays. It deflects them, and we will have some period when the geomagnetic field of the Earth will be very low, and this may give rise to the changes of biodiversity of our planet. This is another. So if we will not talk about periodicity, we have such events like asteroids and so on encountering with our planet, which can produce huge devastation and changing of our environment. But it is not periodical, it is stochastic. And another periodic changes, it is a movement of our solar system through the arms of our galactic. Inside the arms, we have the larger concentration of matter, and so the lower flux of the cosmic rays. And we know that cosmic rays do have effect on the cloud coverage and the temperature on our planet. So there are some theories, I not developed this, but I have seen publications that just ice period and higher temperature periods were changed with the periodicity of passing of solar systems through the arms of the galactics. Between the arms we have lower, so higher flux of cosmic rays. Inside the arm, lower flux of the cosmic rays. This is the other source of the variability. But all these things are more speculations than science. We should make more investigation to say something definite. But your question was what I think about this. I told you about the
I agree. We need more investigation.
Possible reasons of periodicity in
We can start with
life.
We can start with Moon and Mars, looking if there's a seismic activity there. Be interesting to see if there's a similar activity right now on other planets.
Yes, but it is not so easy.
No, but that's
yes,
that's human civilization.
You are young, so before more interesting information, and probably next probes would be able to investigate other planets of our system.
Depends if we have politicians who just keep spending money on bank bailouts and not on science and investigating the solar system, then we have a definite problem for that perspective. Yeah. All right, thanks very much.
Thank you. Thank you.